Our next reaction is one that's going to form new functional groups for us as the product, and these functional groups are going to be imines and enamines. An imine is a functional group that looks like this. An imine is a functional group that looks like this, where we have a nitrogen-carbon double bond, and my nitrogen is bonded to another alkyl group, and in total my nitrogen is bonded to 2 carbon-containing groups. My enamine is a functional group that looks like this. I have a nitrogen that's in a single bond to 3 carbon-containing groups, and one of those carbon-containing groups is an alkene. In my enamine, I have a nitrogen that's in a single bond to 3 carbon-containing groups, and one of those carbon-containing groups is an alkene. The alkene and the amine is the foundation for my enamine functional group. In the enamine, it's this carbon right there where I have my carbon-nitrogen single bond and my alkene. That's the carbon of my original carbonyl where all of the chemistry will take place. In my imine, it's this carbon where I have the carbon-nitrogen double bond. That is the carbon of my original carbonyl. That is the carbon where all of the chemistry takes place. When I look at the reactions for imines and enamines, the reactions for ketones and aldehydes work the same. If I have a ketone like this one, or an aldehyde, when I treat this ketone with a primary amine, like this one, in the presence of a trace amount of acid, and we'll talk about the pH of the reaction in a moment, the product that I get out of this reaction is an imine. That looks like this. My imine has originated out of a reaction where the amine that underwent the reaction was a primary amine or one that was bonded to one alkyl group. For the formation of an enamine, I'm going to take a ketone like this one or an aldehyde. The reaction would work the same. And in order to form the enamine, I'm going to undergo a reaction with a secondary amine like this one in the presence of a trace amount of acid. And the product that I get out of that reaction is my enamine. Which looks like that. The foundation for my enamine functional group is the fact that this reaction took place with a secondary amine. Remember that in the imine, all of the chemistry happens at that carbon right there. And remember, for the enamine, all of the chemistry that's going to happen is going to happen at that carbon. You should be able to understand why we see this difference in reactivity between primary amines and secondary amines as you work through understanding the mechanisms for these reactions. Before we get into the mechanism of this reaction, I want to mention the pH. And the pH of this reaction is very important. Because in this reaction we have amines, like this one. And what we know about amines going all the way back to the very beginning of the year is that amines are very good bases. So that in this reaction, if I have a lot of acid around, what's going to happen is that my nitrogen is going to pick up a proton and it's going to protonate. And when I protonate that amine and form this ammonium ion, the problem is that in my reaction, this ammonium ion is no longer a nucleophile. Because that lone pair on the nitrogen that makes it such a good nucleophile has now been used to pick up this proton, and so this species is no longer nucleophilic. So if I run this reaction with a lot of acid present, what I will do is I will simply protonate all of my amine, and I'll have no amine left to act as a nucleophile in the reaction. So I have to be very, very careful with the pH in this reaction. The optimal pH for this reaction is 4.5. And while we need the amine in the beginning of our reaction to not pick up this proton, when we form a tetrahedral intermediate in this reaction that looks like this, we need the acid around in order to be able to kick off this oxygen-containing leaving group. So this protonation must happen in order for the reaction to progress. That's going to allow us to lose that group and ultimately allow us to make our product, which in this case would have been an imine. So overall, the pH of this reaction is very important because we need the acid for the tetrahedral intermediate to collapse, but we can't have so much acid around that we interfere with the ability of the amine to act as a nucleophile. So our optimal pH for this reaction is 4.5.